Good morning, my academic friends. Today I want to talk about the fundamental building blocks of algebra. So there's one area of math that I hope you're pretty familiar with, and we call it counting. Counting is useful for keeping track of how many things you have. You might have 5 fingers on your hand, a herd of 20 sheep, or 10 rocks. It's not difficult to see how it might be useful to give these amounts names, and we call those numbers. So as you know, we have these things called numbers, and we use them to quantify different amounts. Those amounts can be real, like the number of stones that you have, or abstract, like the number of elements in an imaginary set. Once you've developed numbers, it doesn't take a huge stretch of the imagination to go from counting them to performing simple operations on them, like addition and subtraction. Even though it might not be something you think about on a regular basis, addition and subtraction are just glorified ways of counting. You count up the amount you want to add, and you count back the amount you want to subtract. 1 plus 4 is 5. 5 minus 3 is 2. Once you have addition and subtraction, the next logical step is multiplication and division. Multiplication is just a glorified version of adding. I'm literally doing 2 3 times, or 3 2 times. So 2 3 times, or 3 2 times, is 6. And obviously you know this, but I'm just enumerating all of the basics so that you can see algebra is really as easy as counting. I'll let you think about how you can build division from the ground up. Multiplication and division give way to more complex operations, like exponents and roots. As you know, exponents mean that you're multiplying 2 by itself 3 times. So if exponents are just fancy multiplication, and multiplication is just fancy addition, and addition is just fancy counting, exponents is really just fancy counting. Just really fancy counting. I'll leave those collection of operations over here for now. What do you do if you know you have a number, and you know you want to do something to that number, but you don't know what that number is? So we invent these things called variables that represent numbers that we don't know. Unknown numbers are commonly represented by an x, a y, or an n. I think n stands for number, but I'm not sure. But the fact that they're from the standard alphabet doesn't really matter. They're just placeholders, so you can use any symbol you want, as long as people know what you're using it to represent. So the big question of algebra is, how do we apply elementary operations to numbers that we don't know? And when we do apply those operations, what sort of structures and patterns come out of that? Now your teacher, and we all know how stupid they are, might call some of these structures and patterns rules. But they're not rules in the sense that some mathematician just arbitrarily made them up. They're logical. They come from counting. And everybody knows how to count. So when you're familiar with the terrain of math, and you start to notice these structures and patterns, you invent different classes, different objects of things to help you study them. So you develop these things called expressions, which are just combinations of variables and operations you do to them. For instance, you have a number that you don't know, you're going to square it and you add 2 to it. Then expressions give way to functions, which you can conveniently input numbers into. Then, a brilliant French mathematician and philosopher in the 1600s invented the Cartesian coordinate system. We usually use it to graph things. We use this system to graph functions. Before I go, I want to leave you with a quick example to show you that the rules that your teachers just feed you really come from logical thinking, and they make sense when you just think about counting numbers. So we have a number we don't know, let's call it x, and we raise that to the power of another number that we don't know, we'll call that a, and we raise that whole expression to another number, b, and we need to figure out, how does this work? What do we do with this? We could either go to our textbook and look up the rules that your teachers just throw at you, or we could just think for a little bit. What does this mean? You're taking a number x, and you're multiplying it by itself a times. Since we don't know what a is, we just have to say we multiply x by itself until we get to a. The ellipsis points represent all the a's in between. Now recall the original expression. We're taking this expression, which is just this, and multiplying it by itself b times. So now we've multiplied x times itself a times, and then we're going to multiply that by itself 1 times, 2 times, b times. So let's take a step back and see if we can develop a rule from this. Not just accept what your teacher says. So we have a grid of x's, and each one of these x's is being multiplied by the next x. This grid is a wide and b high. So how many x's do we have? Just like any time you have something that's a certain amount wide and a certain amount tall, to figure out how many you have inside of it, you just multiply those dimensions. So we've multiplied x by itself a times b times. For instance, if a was 4 and b was 2, we would have a 4 by 2 grid. There's 8 total. So we multiplied x by itself a times b times. So we can come to the conclusion that this equals this. And what were we really doing? We were just counting x a times and then counting that b times. So algebra is as easy as counting, and everybody knows how to count. Thanks for watching. Click over here to subscribe. I'll be making more math videos, as well as physics, philosophy, and really any academic subject videos.